Today, I'm presenting a case that's using an aspherical lens to uniformize a laser beam into a very thin profile. So you can see this light is within this Gaussian distribution, and the light original light profile looks like this. And if we want a very thin and uniform light profile at the image plane, so we need some of the higher adjusting power of the spherical lens. So, and we also need to define the Gaussian beam very accurately from the emission side. So the Gaussian beam is defined with those three key parameters with like the waist here is W omega Z, and is theta, and this is the divergence angle, and the ZR is the Rayleigh range here. When we have those definition input in Zmax, and we can have the incident light that is defined here. And when we calculate the incident, the distance from the thickness here, the thickness is the calculated like here. And we are using this thickness to put in this model, and here we ignore the from the waist location to the laser power. If we enable the laser waist location, so this is very big distance there. So when we have ignored that, so we can't see it clearly. So then, so this model is just started from the waist location here, okay? And then we want to have this light is homogenized at 1 meter wave, that's 1,000 millimeter. So here we have defined the light with its output, and you can see the light output is here, okay? And the output, we have divided this output in 40 steps, and to put the memory function here, you see, using REAY. REAY basically is controlling the output angle in y direction. That means you can control the y direction relative to the optical axis to make a very collimated light, and to make it homogenized as the image plane. Okay, and from here, the numbers, the steps that are used in this collimation is calculated like this. And when we have this calculated coordinates, so it is input into the memory function in 40 steps, okay? And this shows the original input light beam profile. That is, can see from here. This is from the object one, surface number one. So this is not so uniformity. So after this collimation and the optimization from the memory function, it is optimized for this collimating lens. And we have traced the light at the imaging plane. You can see the light profile at the image plane looks like this. So the majority of the light profile are encircled into plus minus 0.1 millimeter. So we can also track this encircled energy here. You can see this is to put the light at a very thin area. those of the calculation are coming from this merit function, okay? And you see this light is the radius of the light energy is encircled in less than 0.1 millimeter here. So this case shows that even a spherical lens, that to reform a random or regularly distributed Gaussian light, and how it can be reformed in the image plane with a very thin optical profile. And another thing is worthy to point out is this aspherical lens has used from second term to 16th term. And if we using the second term, it may maybe a little bit far away from the manufacturing template. So in this case, I used a zero, just wipe out the second term of the aspherical parameters. So I just use it from 4th to 16th. So hopefully we can have a smooth manufacturing experience for this lens.